Hello and welcome. In this video, we're going to take a look at a couple more examples of functions, and we're going to propose a more rigorous way to test whether a relation is a potential function or not. So we're going to first of all remember that a function, capital F, between a and b is a relation between a and b. So basically it means that it's a set of ordered pairs, and for every element x within a, there is a corresponding y within b such that that ordered pair is inside the function. So in other words, that for each input there's an output, and that input-output pair is within our set that is the thing that we're calling the function. If you have two ordered pairs with the same x value, first ordered pair has y of y1 and second ordered pair has a y of y2, then for this to be a function we have to make sure that that input repeated twice points to exactly the same output. And we've often thought about that as the vertical line test. But basically if there is an input for which there are two or more different outputs, then that's not a function. So as one practical example, let's suppose that we have a database. And we have a database of names. So people's names. And on the output side, we have, or in our other set, we have social security numbers. Now, if we think about the domain to be the set of all names, and we think about the range as the set of all social security numbers, we have to ask ourselves, does this relation of there being a name in here, is this going to satisfy the definition of a function? So for instance, let's just say that I have an element x here, and that element we're going to name John Smith. Now, we said that our domain is the set of all names, so if I write this function as capital F, because we have to remember that F is a set, it's the collection of all such ordered pairs, then I would, have, and sometimes we denote this R initially to say that this is a valid relation, it just may not be a function. So it doesn't really matter what letter we use. But R is equal to, and it's going to be the set of all pairs inside of the set. So first of all, we're going to have John Smith. And John Smith may have a social security number in here that we'll just refer to as 1, 2, 3, 4, 5, 6, 7, 8, 9. Now we have to ask ourselves, is that social security number unique to the name John Smith? Well, there's probably a lot of people out there named John Smith. And if not John Smith, then some other name like Max Powers. Probably lots of Max Powers out there. Probably lots of people with the same name in general. And so I don't think I could say that for this particular X, for that particular X, I cannot say that when I look up the name John Smith that I'm only going to get one social security number back. In all likelihood, there's probably going to be multiple John Smiths in here, and another one that has maybe 2, 3, 1, 4, 5, 6, 7, 8, 9. So within my relation, I'm going to have this added ordered pair with John Smith with this 2, 3, 1, 4, 5, 6, 7, 8, 9. And of course the set would go on for a long time depending on how big our domain and range are in this case. But I cannot say with confidence that the relationship between names and social security numbers in this order, I cannot say that this is a function. So we'll say that. We'll say this is not a function. Now, we could argue in number 1, the first qualification is that every single x inside of this domain that we define to be A, for every name in here, there's going to be an associated social security number, at least in the majority of cases. Now, if we flip that around and we let our domain represent the set of all social security numbers and our range represent the set of all names, the story changes a little bit, because now the social security number 1, 2, 3, 4, 5, 6, 7, 8, 9 uniquely points to our output, in this case the person's name, who is John Smith. So in this case, every single social security number, I can arguably, every social security number has exactly one name, or excuse me, has a corresponding name. And that satisfies my condition 1 here. For every element in the domain, there's a corresponding value in the range. And then secondly, every social security number links to exactly one name. And so condition 1 and condition 2 are satisfied. Therefore, this is yes, a function. Now that relation is, the relationship that we're describing could also be stated in set notation. So here's our set notation, and it looks like we have a set of names and perhaps their ages. So A is the set of names, and B is the set of age, or all of the possible ages. So we do see here that every single name does have a corresponding age. It's not like Dave, comma, and then nothing. Dave, comma, 17 says that Dave is 17 years old. So these could be, if you're writing a computer program, you may actually be passing tuples back and forth between functions and hoping to get the desired output. Now a little bit, the visual way in which I could draw this is again to think about my domain, which is going to be the set of all names, Dave, Sue, and Fred. And then my range is going to be the set of all possible ages, which are 17, 21, 35, and 18. So it turns out that Dave has an age of 17, so we can link Dave, the input, to the corresponding age of 17, which is the output. We can say Sue is 21. We can say Fred is 35. And wait a minute, we have an extra Dave here, but there's a mismatch in the ages, meaning that an input of Dave, if this were a computer function and it took in the person's name and it gave as an output their age, there would be a little bit of confusion, right? There would be a return error because Dave actually corresponds to two different ages, so this may not be the best way to write a function. Of course, we'd want to use first name, last name, or have other identifiers. But this is really why having constructs that are not functions in computer science are problematic, because a function has to be able to return something distinctly. So this, to be able to say that R is not a function from a computer science standpoint can be problematic. We've got to have a way to ensure that all of our inputs, each of our inputs, not only has a corresponding output, but that it has a distinct corresponding output. All right, let's move on to something a little bit more formal. Let's say that we wanted to actually establish a more concrete argument to say that x squared plus y squared equals 1 is not a function. Now we've already seen this. It doesn't pass the vertical line test, right? That basically a circle has this ability for a given input, say that one right there, that gives us two outputs. It gives us one right here and it gives us another one right here. So for that input of y equals blank, we're going to have two different outputs, and that's where the problem occurs. Now x is in the range between -1 and 1, basically meaning that for the unit circle we're going to have x can go as far as -1 and as far as 1 to the other side. Now y is going to be an element of the set from -1 to 1 as well, because this guy fluctuates. Y can go anywhere between -1 and +1. Okay, so we know that every single input, if I plug in an x, it will definitely produce a y. For example, if I give this function x equals something in the domain, it has to be in the domain, x equals 0, then x squared, which is 0 squared plus y squared equals 1, will have y equals plus or minus 1 as an output. But really, that's also our proof that this is not a function, because we have an input for which there's more than one output. So basically, by counterexample, x squared plus y squared equals 1 does not satisfy condition 2. And so, therefore, we could say x squared plus y squared equals 1 is not a function. How do we prove that something is a function? Showing that something is not a function is a matter of constructing what we call a counterexample. Counterexample means that it's an example that counters what it might be. So we're trying to counter the idea that this is a function by providing an example for the counter. And so if you're trying to disprove something, oftentimes you just need to find one example where that statement fails, because in logic, as we'll learn later on, a statement is either true or false. There's no fuzzy logic. It's 0, 1, false, true, no, yes. It's going to be a binary situation whenever we deal with this kind of logic. Well, let's take a look at one more. So if I take a look at, say, the linear function 2x plus 3y equals 1, we're going to argue that this is a function. So prove 2x plus 3y equals 1 is a function. Well, how do we do that? Well, first of all, we just need to verify the conditions. So condition 1, does every x give us a y? In other words, can we generate at least one y? So one way I could verify this is that if I say let x take on some arbitrary value, some constant. It could be anything. This is just some arbitrary value on the number line, meaning that if I draw my number line here, x could be here, or it could be here, or it could be here, that these are all possible values of x along this number line. On this number line, we have some sort of relative 0, and this number line goes on infinitely in both directions. So let's say you've chosen some x, and without loss of generality, let's just say that it's some value x equals c over here. Well, if x equals c, that means that 2 times x, or 2 times that c value, plus 3 times y equals 1. Now, what I'm trying to do here is establish that we can find a y. So if I do a little bit of algebra here, I solve for y, I get 1 minus 2c over 3, and that really concludes or verifies that given a value of x, I can find a corresponding value of y. What's that value going to be? Well, it's going to be the difference between 1 and 2c, and it's going to be 1/3 of that value. So every x, if x equals c, then y equals 1 minus 2c over 3. For all c, for any value of c. There's no value of c that you can plug in to this position right here and have a failure. You're not ever going to get an undefined value. Subtracting 2 times some constant can be done from 1 all the time for any real number. Okay, so that's condition 1. Basically, just pick some arbitrary value for x, make sure that you can get a value for y, and then say, well, if x equals that constant, then y is going to equal blank. Step 2 is to say, suppose x, y1, and x, y2 are both points along 2x plus 3y equals 1. Better yet, let's say that we've isolated some value of x. So we'll just call this cy1 and cy2 are both points along 2x plus 3y. So all we know so far is that if we were to graph 2x plus 3y, which would, let's see, look something along the lines of a line that is decreasing from left to right. Okay, so if this is the line 2x plus 3y equals 1, what we've basically said here, suppose for a moment that there is a value of x that generates something called a y1 and it generates something potentially else called a y2. So we know that this argument is going to produce the statement that y1 equals y2 because, for instance, if I let x equals c be some value over here, I know that the value of y is one distinct output. So what we're gonna determine is that y1 and y2 have to be the same thing. There's no way this function for one given input can generate two different outputs. So here's one way to do it. One way to do this is to say, well, if cy1 is a point along this line, let's first focus on this guy here. What that would mean is that 2 times c plus 3 times y1 equals 1. Right? That would be the statement that would be true. That in other words, there is some value of x and some corresponding value of y such that when you double x and you triple y and add them together, you're going to get 1. On the other hand, we have this other point over here that we're claiming is on the line as well. We know it's going to be the same point, but that's what we're trying to set out to mathematically show. Basically, that for any arbitrary x, we're always going to get one unique value of y. So we can say the same thing here. If we plug in this ordered pair into this equation, we have that 2 times that value of x plus 3 times that value of y equals 1. So since both of these equations are equal to 1, that is 2c plus 3y1 is equal to 1, and 2c plus 3y2 is equal to 1, well, that means they're equal to each other, right? Because they both have a weight of 1. So 2c plus 3y, 2c plus 3y, which equals 1, and 2c plus 3y2 is also equal to 1. We can set those two equations equal to each other. 2c plus 3y1 equals 2c plus 3y2. And watch what happens now. We see that on both sides of this equation, the two c's will cancel, and now I'll be left with the statement 3y1 equals 3y2. And now when I do division by 3, I see that this leads exactly to the conclusion that y1 equals y2. Therefore, for every x, there is exactly one y. And we should have also specified that x, because this is a linear function and this line goes on infinitely in both directions, x is just some number between negative infinity and infinity. You can't include infinity because infinity is not a number, but we can say it's somewhere infinitely in either direction. Now the value of y, right, because this line goes like this, however you want to look at it, it's going to go infinitely up and it's going to go infinitely down. So this thing is just going to continue ascending upward and descending downward. So that means y is also going to end up being some number between negative infinity and infinity. And what we're saying here is that for any x that you pick in this domain, you're going to be able to generate y within this range right here. Domain and range. And so basically what we just established is to say, therefore, 2x plus 3y equals 1 is a function. Hopefully that's been helpful as an example of how we do proofs rigorously when we talk about functions. And these are useful things to be able to do, because in the scope of computer programming, if you're claiming that every single input's going to produce one output, you can actually use your pseudocode to verify these types of things.